Yeah, so hello everyone, and welcome to the first lecture of the first mini course of this summer school. And we are very pleased to have with us Sarah Penington, who is a prize fellow at the University of Bath. And so today, on Thursday and on Friday at this time, she will tell us about free boundary problems and branching particle systems. And a copy of the lecture notes and slides is on the course website, on the school website. The link is in the chat, so you can have them open separately if you like. And Sarah, please, floor is yours.
So thank you very much for the invitation to give this this mini course. It's very nice to participate in another PIMS Summer School, even if it's remotely. So this mini course is going to be about branching selection systems. So these are particle systems in which the particles can branch, so they can split into multiple new particles, and they also move around in space according to some random process. And there's also some kind of killing rule that means that when a particle in the system branches, then one or more particles in the system are killed, and so the total number of particles in the system stays constant. And these systems can be seen as toy models for a population under selection. So you could think of the location of a particle, which corresponds to an individual in a population, as representing the evolutionary fitness of the individual. And we choose the killing rules in such a way that the particles that are killed correspond to the least fit individuals in the population. And these are not super realistic models for a real population, but the idea is that by understanding the behavior of these toy models, we could eventually hope to understand more realistic models. And also they're just mathematically really nice processes to study. So branching selection systems were introduced in the physics literature by Brownian and Derrida in the 1990s. And there are quite a lot of recent results and also lots of open conjectures about their long-term behavior. And some of the recent results are about linking these branching selection systems to PDEs, partial differential equations, called free boundary problems. So what I want to tell you about in this mini course is how we can prove things about the behavior of the particle systems, what we can learn about the behavior of the particle systems using the links with these free boundary problems. So today I'm going to be talking about a branching selection system called n-particle branching Brownian motion, or NBBM for short, and a related free boundary problem. And then in the next lecture, I'm going to talk about a related system called Brownian Bees. And for the Brownian Bees, you can actually determine the long-term behavior of the system using a connection with another free boundary problem. And then in the last lecture, I'm going to talk about some other branching selection systems, including the n-particle branching random walk. And I'm going to try and give an overview of some results and conjectures about their long-term behavior. And for parts 1 and 2, then the proofs come from a mixture of probability and PDE ideas. But in the lectures, I'm going to focus on the probabilistic ideas in the proof, and also how the PDE results are used, rather than going into the PDE proofs. So this is the first particle system that we're going to talk about. So it's called n-particle branching Brownian motion, or NBBM for short. So the particle system consists of n particles that move around on the real line according to independent Brownian motions. And each particle is also carrying a clock that has an independent amount of time on it that's exponentially distributed with rate 1. And at the end of that amount of time, so when the clock rings, then the particle branches into 2 particles. But each time a particle in the system branches, then the leftmost particle in the system is killed. So there are exactly n particles in the system at all times. So on the right, I'm going to show you what the NBBM might look like for n equals 5. So we start with 5 particles somewhere on the real line, and time is going to go up the slide. So the particles are going to move around according to independent Brownian motions until one of them decides to branch. So that might be this green one here. Someone's just asking a question about what if there are multiple leftmost particles. So essentially it doesn't matter, because then you can just kill one of them arbitrarily and it doesn't actually matter which one you kill. That's kind of the lazy answer. The particles are moving around according to Brownian motions until one of them decides to branch, so maybe this green one. And then what we do is see which particle is furthest left. So that's this red one. And then that particle is killed, and the green particle branches into two, and all the other particles continue to move as Brownian motions. And then we keep going until another particle decides to branch, so maybe this green one here. And then we see which particle is the leftmost particle. So that's the red one, and the red particle is killed, and then the green particle branches into two. And then maybe this green one decides to branch. So in this case, the particle that's branching is actually the leftmost particle. So I guess this is slightly related to the question. So when the leftmost particle branches, then its two offspring, one of them is immediately going to be the leftmost particle in the system. So what we do is we just say that one of its offspring is immediately killed, and so essentially nothing happens. So it still continues as just one particle, and the other four particles are going to continue moving according to Brownian motions and so on. So at all times we've got exactly n particles in the system. So this model was introduced by Pascal Maillard in 2012, and it's a natural continuous time analog of discrete time branching selection systems introduced by Brunet and Derrida in 1997. And I'll talk more about some discrete time processes in the last lecture. And as I said, it can be seen as a toy model for a population undergoing natural selection. So you could think of the position of a particle on the real line as representing its evolutionary fitness. So particles that are further to the right have a higher evolutionary fitness. And the way that the model is defined means that the individuals with lowest fitness are the ones that are killed. And what we want to understand about this model is the long-term behavior when we take a large number n of particles. So we'd like to understand the speed at which the cloud of particles moves to the right, and the shape of the cloud of particles, and also the genealogies. So if we sample some particles and look at their family trees, then what do they look like? So I'm going to talk more about genealogies in the last lecture, and either at the end today or maybe in the second lecture, I'll talk a little bit about this speed and shape question. But what I mostly want to talk about today is the fact that if we look at this NBBM on a fixed timescale, and we let the number of particles n go to infinity, then the density of the particles converges to the solution of a free boundary problem. So first of all, I just need a bit more notation for the NBBM. So I'm going to write xn of t for the vector of particle positions in the NBBM at time t. So x1n of t up to xnn of t. And I'm going to write lnt for the minimum for I in 1 up to n of xin of t. So lnt is the leftmost particle position at time t. And then this is the free boundary problem that's going to turn out to be related to the NBBM. So we're going to have a probability density U0 that's going to be, so someone's asking in RD, so this is all in R. The particle system that I'll talk about in the second lecture will be in RD, and I'll say what norm we're using there, but here this is all in R. So it's all one-dimensional Brownian motions. So we've got this probability density U0, which is going to be the initial condition. And then we've got a pair of unknowns, U and L. So U is a function of time t and location x, and L is just a function of t. So we can think of L as being an unknown moving boundary. And we want U and L to solve this system of 4 equations that I'm going to refer to as FBP1. So the first equation is saying we want U to solve a PDE for X to the right of LT. And then the second equation is saying that we want U to satisfy a boundary condition at LT. So we want U of T and LT to always be equal to 0. And then we want the integral of U at time t from LT to infinity to always be equal to 1. And we want the initial condition to be given by U0. So at some fixed time t, then this picture on the right is trying to show you what U might look like. So it's equal to 0 at LT. And the integral of this curve has to always be equal to 1. So first of all, it's not at all clear initially that a solution to this system of equations should exist, but it turns out that it does exist and it's unique. And then it also turns out that if we think of our NBBM with a very large number of particles n, then U of t and x is roughly the density of particles in the NBBM at location x at time t. So what I mean by that roughly is, I mean, we would look at the number of particles in a little interval around x at time t, divide that by the length of the interval, divide by n, and take the limit as delta goes to 0. And also that LT is, we can think of as being roughly the position of the leftmost particle in the NBBM at time t, which we call LNT. So if we think of U and L in this way, then why do we get this system of equations? Well, if we take x to the right of LT, so x strictly bigger than LT, if we're thinking of LT as being roughly the position of the leftmost particle, then if you're a bit to the right of there, then particles are just happily moving around according to Brownian motions and branching into two particles at rate 1, and they're not being killed. What we should get for the for du by dt, if u is the density, we should get a smoothing term that comes from the motion according to Brownian motion, which turns out to be a half Laplacian of u, and then we should get a plus u because at rate for each particle at rate 1, a particle is being added to the system. And then if we look at so that tells us that we should get the first equation. Then for the second equation, if we look at x equal to the position of the leftmost particle at time t, which we're saying should be roughly LT, then at that position, particles are being killed because they're becoming the leftmost particle. So the density of particles there should be 0. So we should have that U of t and LT is equal to 0. And that's the second equation. Then the third equation is coming from the fact that the total number of particles in the NBBM is always constant, equal to n. So that means that if you give each particle a mass 1 over n, then the total mass of particles is equal to equal to 1. So the integral of the density of the particles should just be the total mass of the particles, so it should always be equal to 1. So that gives us the third equation. And then the fourth equation is just an initial condition. So that's a sort of very rough heuristic for why we should get this free boundary problem. But now I want to show you a rigorous result. So this is a hydrodynamic limit result.
Yeah, so there is a
which
question in the chat, by the way,
yeah,
about whether this is connection.
So, I mean, yes and no. It's a hydrodynamic limit, so maybe I'm going to be more specific about the hydrodynamic limit now. So maybe that will answer the question. So this is a theorem of De Masi, Ferrari, Prositti, and Soprano-Loto from 2017. So let's suppose that we start with particle locations at time 0, which are IID with some density U0, where U0 is the initial condition for our free boundary problem. Then if we take an x and a positive time t, and we look at the proportion of particles at time t which are to the right of x, so 1 over n times the number of particles in the NBBM which are, have positions greater than or equal to x at time t, that converges almost surely as n goes to infinity to the integral from x to infinity of u at time t. Or in other words, roughly speaking, the density of particles at location y converges to u of t and y. And in some ways, this result built on an earlier result of Duret and Vremenick from 2011. So they also proved a hydrodynamic limit result for a branching selection system in continuous time, where each time a particle branches, then the new particles make a jump from the location of their parent, and particles don't move apart from making these jumps after branching. And in this system as well, the leftmost particle is killed each time a particle in the system branches. So I'm going to spend most of the rest of this lecture talking about the proof of this hydrodynamic limit result. But the key idea to get started on the proof is that on short time intervals, you can sandwich the NBBM between two different processes that are easier to control. And those processes are actually both going to be just branching Brownian motions, BBMs, with different initial conditions. So I'm going to start with a bit of notation for branching Brownian motion. So in a branching Brownian motion, particles moving on the real line according to independent Brownian motions, and each of them independently is branching into two particles after an exponentially distributed waiting time with rate 1. So we're going to write x plus of t for the vector of locations of particles in the BBM, branching Brownian motion, at time t. So we'll write n plus t for the number of particles in the branching Brownian motion, which will increase over time. And then we'll write x1 plus of t up to x plus n plus t of t for the locations of the particles. And we won't be too worried about the ordering of these particles in this vector. So you could use an Ulam-Harris ordering, but it's not going to matter what the order is in this vector. And we'll write h plus of t and x for 1 over n times the number of particles in the branching Brownian motion at time t, whose locations are to the right of x. So 1 over n times the number of locations to the right of x, number of particles to the right of x at time t in the branching Brownian motion. And then, so I already said that we would write xn of t for the vector of locations of particles in the NBBM at time t. But actually, at some points, we're going to care about the ordering of particles in that vector. So this is going to be a convenient ordering. So at time 0, we're going to give each particle a different label from the integers 1 up to n. And then we'll say that when a particle branches, so let's suppose that the particle with label j branches, then if just before the branching, the leftmost particle in the system has label k, then that's the particle that's killed. And so we say that the two new particles are going to be given labels j and k, because the label k has now become available. So in the special case where j is equal to k, then this is what I mentioned before, that if the leftmost particle tries to branch, then effectively one of its two offspring particles is immediately killed. So nothing happens in this case. And the labels don't change between branching events. So one way that you can actually think of this branching event as happening is that the particle with label k jumps from its old position, which was the leftmost particle position, it jumps to the position of the particle with label j that branched. And no other particles move in the branching event. And we're going to write hn of t and x to be the equivalent of h plus. So it's going to be 1 over n times the number of I less than or equal to n, such that xin of t is greater than or equal to x. So it's the proportion of particles in the NBBM at time t, which are at positions greater than or equal to x. So as I said, we're going to have we're going to sandwich the NBBM between two different branching Brownian motions. So first, we're going to do the upper bound coupling, because that's significantly easier. So at the top of the slide, I'm just reminding you of the definitions of H plus and Hn. And then this is our upper bound coupling. So let's say we have a vector x in Rn. Then there exists a coupling of the BBM and the NBBM such that under the coupling, the initial particle configuration of the NBBM is given by X. So there's one particle at X1, one at X2, and so on. And the same for the BBM. So they both have initial particle configuration X. And Hn of T and X is less than or equal to H plus of T and X for all times T and all locations X. So the way that we prove this is actually doing okay, so someone's asking what's the difference between the BBM and the NBBM. So in the BBM, particles move according to Brownian motions, they branch, they're never killed. In the NBBM, whenever a particle branches, the leftmost particle in the system is killed, so there are always exactly n particles. So the number of particles stays constant in the NBBM, whereas in the BBM it grows. So the way that we prove this upper bound coupling is actually we do what's probably the most natural construction of the NBBM from the BBM. So we just take a BBM and we successively remove the leftmost particle at each branching event. So now I'll be a bit more explicit about what I mean. So we're going to have a particle system that consists of red and blue particles. And at time 0, we're going to have a particle configuration given by the vector x. So we'll have a particle at x1, a particle at x2, and so on. And all n particles are blue. And all the particles move according to independent Brownian motions, and they all branch independently at rate 1. And when a blue particle in the system branches, then its two offspring particles are both colored blue. And then the leftmost blue particle in the system is recolored red. And whenever a red particle branches, the two offspring particles are both colored red. So then the system of blue particles is an NBBM, because in the blue particles system, each particle moves according to an independent Brownian motion. It branches at rate 1 into two offspring particles, and the leftmost particle in the blue particle system is removed from the blue particle system because it's turned red. And the whole system of particles forms a BBM because each particle is branching at rate 1 and moving according to a Brownian motion, and no particles are ever actually killed. They're just turned into different colors. So that means that under this coupling, then if we look at the number of particles in the NBBM that are to the right of x, then that's just the number of blue particles that are to the right of x, which is certainly at most the number of particles in total which are to the right of x, which is the same as the number of particles in the BBM which are to the right of x. So we have this inequality, and then if we multiply each side by 1 over n, and we go back to the definition of h plus and hn, then what we get is exactly this upper bound for hn.
Yeah, so the blue particles are a subset of the BBM, but they are not going to be the rightmost.
Not necessarily, because a red particle could a particle could get killed by doing badly, but then later on it could do really well. Yes, exactly. So this gives us an upper bound on hn, and now we want a lower bound. So we're going to need a little bit more notation. So I've still got h plus and hn, the definitions at the top of the slide. And now for a vector x in Rm and another vector x primed in Rm primed, we're going to write that x is greater than or equal to x primed. And what I'll say is that x dominates x primed if and only if. So here I'm abusing notation a bit, and I'm sort of writing x as if it was a set rather than a vector. But what I mean by this is the number of entries in the vector x which are greater than or equal to little x. And I want the number of entries in x greater than or equal to little x to be at least the number of entries in x primed which are greater than or equal to little x for all little x, all real values little x. And it's not too hard to convince yourself that this happens if and only if m is greater than or equal to m primed, and also there's a reordering of the entries of x such that each entry of x primed, so for each I less than or equal to m primed, each xi primed is less than or equal to a different entry of x. So now we can state the lower bound coupling. So let's suppose that we have a vector x in Rn and a vector x plus in Rm, and that x dominates x plus. So in particular, that means that m is less than or equal to n. Then there exists a coupling of the n BBM and the BBM such that under the coupling, the initial particle configuration in the n BBM is x, and the initial configuration of the BBM is x plus. And for each non-negative time t, hn at time t is at least h plus at time t if nt plus is less than or equal to n. So nt plus was the number of particles in the branching Brownian motion at time t. So this is saying that hn is at least h plus, as long as until there are more than n particles in total in the BBM. And by the definition of h plus and hn, and by this definition here, then we can see that hn is greater than or equal to h plus if and only if xn at time t dominates x plus at time t. So the way that we prove this, so we're going to prove this by first there's a claim from which the lemma follows fairly easily. So let's let tau I plus be the ith branching time in the BBM x plus. So the claim is that if we take any vector x in Rn and a vector x plus in Rm plus, where x dominates x plus, then we can couple the NBBM and the BBM in such a way that the NBBM starts with particle configuration x and the BBM starts with particle configuration x plus, and xn dominates xn of t dominates x plus of t for all t in, and then it's the time interval 0 up to the first branching time in x plus if x plus starts with fewer than n particles. So this is including the time tau 1 plus, but if the BBM starts with exactly n particles, then this only holds up to, but not including the time tau 1 plus. So we're going to prove the claim on the next slide. But first, let's assume the claim and see why the lemma follows from the claim. So first of all, let's suppose that in the lemma that m is equal to n. So we only want to prove that xn of t dominates x plus of t until there are more than n particles in the BBM. And so if m is equal to n, then we only need to prove that this holds up to the first branching time, which is exactly what we have from the claim. We have this second part of the claim. But if the BBM instead starts with fewer than m particles, then the claim will tell us that xn dominates x plus up to and including the first branching time. So then we can use the fact that xn dominates x plus at the first branching time to apply the claim again on the time interval from the first branching time until the second, and so on until we get to the point where we actually have more than n particles in the BBM. So that will be at time tau plus n minus m plus 1. So essentially, the lemma follows really pretty easily from this claim. So now I'm going to try and show you a proof of the claim. So this is going to be probably the longest proof in the course. So yeah, please bear with me. So this is the claim that I've just got at the top of the slide. So the first thing, so the claim is essentially reducing what we need to prove to just proving that one process dominates the other up to the first branching time of the BBM. So what we're going to do first is assume by reordering the entries in X, if necessary, that xi is greater than or equal to xi plus for all I less than or equal to m. And we're going to let tau I be the ith branching time in the NBBM. And we'll let ji be the index of the particle that branches at that time. And we'll let ki be the index of the leftmost particle just before that branching time. And we're going to couple the branching times in the BBM and the NBBM in such a way that particles with the same index branch at the same time. So that will mean that the first branching time in the BBM, which is tau 1 plus, will be equal to tau I plus, where I plus is the minimum value of I such that ji is less than or equal to m. So the first it's the first branching time at which the particle that branches has index less than or equal to m, and so it's a particle that actually has an equivalent in the BBM. So then what we're going to do is couple the Brownian motions up to time tau 1, so up to the first branching time in the NBBM. So we'll let, for I less than or equal to n, we'll let bi of t be IID Brownian motions starting at 0. And then let's let the position of the particle with index I in the NBBM at time t will be given by xi plus bi of t for t less than tau 1 and for I less than or equal to n. And the position of the particle with index I in the BBM at time t will be just the same thing, but with the starting position given by xi plus instead of xi. And this is for all I less than or equal to m. So that means that for I less than or equal to m, then because xi plus is less than or equal to xi, that means that xin of t is greater than or equal to xi plus of t for all t less than tau 1. And so that means that xn of t will dominate x plus of t for all times t up to tau 1. So then we need to work out what we're doing at the branching time at time tau 1. So we're going to suppose first that tau 1 is not equal to tau 1 plus, or in other words, J1, the index of the particle that branches at time tau 1 is bigger than m. So in that case, at time tau 1, we've got some branching in the NBBM, but nothing is happening in the BBM. And what's happening in the NBBM is that the particle with index K1, which is the index of the leftmost particle just before the branching event. So the particle with index K1 is just jumping to the position of the particle with index J1. So the position of the particle with index I at time tau 1 is either its position just before time tau 1, if I is not equal to K1, or it's the position of the branching particle, so it's the position of the particle with index J1 just before the branching event, if I is equal to K1. So that means that each particle is either staying in the same place or it's making a jump to the right because it was the leftmost particle and it's jumping to the position of another particle. So that means that if we take an I less than or equal to m, then the position of the particle with index I at time tau 1 is at least the position of the particle with index I just before time tau 1, because any jump that it's made has been a positive jump. And then this here tells us that that must be at least the position of the particle with index I in x plus just before time tau 1, which is the same as the position of the particle with index I in x plus at time tau 1, because nothing happens in the BBM at time tau 1. So that tells us that the position of the particle with index I in the NBBM is greater than or equal to the position of the particle with index I in the BBM at time tau 1. So xn at time tau 1 dominates x plus at time tau 1. So now we can just do the same construction on the interval tau 1 up to tau 2 and so on until we hit the first branching time for the BBM, which is time tau I plus. So the same argument will tell us that xin of t is greater than or equal to xi plus of t for t less than tau 1 plus and I less than or equal to m, which tells us that xnt dominates x plus t for t less than tau 1 plus. So now we've got pretty close to what we wanted. So in fact, if we had that m is equal to n, then we have exactly what we wanted, because we just need to prove that this holds on this time interval, but not at the endpoint. So from now on, let's assume that m is less than n. And now all we need to prove is that this thing at the end, so we need to prove that xn dominates x plus at time tau 1 plus. So what happens at time tau 1 plus? Well, we're going to call it time tau just to make the notation a bit lighter. So then the particle, which we're going to call j plus, which is ji plus, the particle with that index branches in both the BBM and the NBBM. And in the NBBM, the leftmost particle is killed. So the particle with index k, what we'll call k plus, which is ki plus. So let's take a k that's less than or equal to m and not equal to k plus. So in the NBBM, any particle that's not equal to k plus, a particle with that index doesn't move at this branching event. So xn tau is equal to xnk tau is equal to xnk just before tau, and then this thing here tells us that this is at least xk plus just before time tau. And then what's the position of the particle with index k plus at time tau? Well, it's the position of the particle that branched just before time tau. So it's xnj plus of tau minus. And again, we can use this to say that it's at least the position of the corresponding particle in the BBM. And then finally, if k plus is less than or equal to m, we can say that xn m plus 1 of tau, well, it's a particle in our NBBM, so it's got to have position at least the position of the leftmost particle just before the branching event. So it's at least at xnk plus of tau minus. And then again, that's at least at the position of the corresponding particle in the BBM. So we can use these three things to get what we want, because so what are the particles in the BBM at time tau? Well, there are m plus 1 particles. So there are the m particles that there were just before the branching event. And then there's an extra particle here at x plus j plus of tau minus. So if k plus is bigger than m, then this inequality gives us m particles which are bounded above by particles in the NBBM, and then this one gives us another one. So we've got m plus 1 particles in the BBM, which are each less than or equal to a different particle in the NBBM. fewer than n particles at time t, and so this bound holds with high probability. So what can we get if we put these things together? Well, let's take a small time delta, and then from this inequality and this inequality, we can say that hn at time delta is between e to the delta g delta and a cut operator. So I'm removing the little n to the minus c because that will only make a small difference, applied to v naught n, and then minus a little bit. And hn at time delta is at most a cut operator e to the delta g delta applied to v naught n, plus a little bit. So then what we can do is iterate this bound. So if we take a fixed time t and we take delta to be of the order n to the minus some small constant, and we choose delta, our specific choice of delta is so that t divided by delta is an integer, then so by iterating this bound, then it turns out that you can get that hn at time little n times delta is between this operator applied n times to v naught n minus a little bit, and this operator applied n times to v naught n plus a little bit. And by our choice of n and delta, then n times delta is t. So this gives us that hn at time t is sort of with high probability sandwiched between two different deterministic quantities. So now we just need to estimate what those are. So I'm just reminding you still of the definitions of these operators, and then this third line is just what we've well roughly showed. And then so to finish the proof of the hydrodynamic limit, we just need two deterministic lemmas. So the first lemma says, let's let v of t and x be the integral from x to infinity of u at time t, where u and L solves our free boundary problem with initial condition u naught. And let's let v naught of x be the integral from x to infinity of u naught. Then if we take an integer n and a small delta, then v at time n delta is sandwiched between this operator applied n times to v naught, which is the same operator we have here, and this operator applied n times to v naught, which is the same thing that we have up here. So I'm not going to say much about the proof of this result, but essentially this result is, you can think of it as being a deterministic version of the upper and lower bound couplings that we had for the NBBM. So this in the middle corresponds to the NBBM, and in a sense these are the upper and lower bound couplings with capital N equal to infinity, then iterated over little n time intervals. Then the other deterministic lemma that we're going to use is one that says that actually these upper and lower bounds are very close to each other. So if we take a function v naught from the reals to the interval 0, 1 and a positive delta and an integer n, then if we take the difference between this thing and this thing, and we take the L infinity norm, then that's at most e to the n delta plus 1 times e to the delta minus 1. So if n times delta is equal to t, and if delta is very small, then this bound is going to be very small. So again, I'm not going to have time to say anything about the proof of this, but the proof of this is actually fairly straightforward. So now how do we use these two results to get our hydrodynamic limit result? So if you remember that in the setting for the hydrodynamic limit result was we had a large number of particles, capital N, and our initial particle locations were IID with density given by U naught. So if we let, so our V naught N here was, so V naught N of X was 1 over N times the sum from I equals 1 to N of the indicator that the position of the ith particle at time 0 is greater than or equal to X. And because of the way that we're defining our initial particle locations, then, and because N is very large, then with high probability, this is just going to be very close to the probability that an individual particle is greater than or equal to x, which is the same as v naught of x by the definition of v naught of x up here in the lemma. So that means that essentially we can just write v naught instead of v naught n in this thing up here. And so that means that with high probability, we have that hn at time t is sandwiched between this operator applied n times to v naught minus a little bit, and this operator applied n times to v naught plus a little bit. And then these two lemmas tell us that v at time n delta is sandwiched between these two things, and the second lemma tells us that these two things are extremely close together. And so both of these two things must be very close to v at time n delta. And so that means that we can write that both of these are approximately v at time n delta. And we chose n and delta so that n times delta is equal to t. So this is telling us that hn at time t, which is of t and x, which is the proportion of particles in the NBBM which are to the right of x at time t, is roughly, with high probability, it's roughly the integral from x to infinity of u at time t. So that's essentially what the hydrodynamic limit says. So I just wanted to end today by saying a little bit about the long-term behavior of the NBBM. So what our hydrodynamic limit result told us was if we fix a time t and we let the number of particles n go to infinity, then we now know what the particle system looks like. But what we'd now like to do is understand the long-term behavior of the NBBM for large n. So we'd like to fix a large n and let time t go to infinity. So one thing that is something is known about is the asymptotic speed of the cloud of particles. So if you remember that we wrote ln(t) for the position of the leftmost particle at time t. So it's known that there's a deterministic speed an, such that if you divide the leftmost particle position by t, and you let t go to infinity, then this converges to an almost surely. And it's also known that an converges to square root of 2 as n goes to infinity. And so for comparison, if you look at the rightmost particle in a BBM at time t, and you divide that by t, then that converges almost surely as t goes to infinity to square root of 2. So essentially, this is saying that if you take the asymptotic speed of the NBBM converges to the speed of the rightmost particle in the BBM as n goes to infinity, which is as you might expect. Then, so in these boxes, I'm summarizing what our hydrodynamic limit result said. So it said that if we take an NBBM particle configuration at time t, and we let n go to infinity, then the density converges to the solution u of the free boundary problem at time t. What's also known, and so you can prove this using Harris recurrence, is that if you fix n and you view the particle configuration from the point of view of the leftmost particle, so if you just look at the displacements of the other particles from the leftmost particle, then the distribution of the NBBM converges to a stationary distribution that depends on n. And then for the long-term behavior of solutions of the free boundary problem, there's an infinite set of traveling wave solutions that have different speeds. But there's a unique traveling wave solution that has the minimal speed, which is square root of 2. And it's conjectured that if you take a solution of the free boundary problem with a compactly supported initial condition, then it converges as t goes to infinity to this traveling wave solution with minimal speed. And what's also conjectured is that if you take n to infinity, then the stationary distribution of the NBBM converges in some sense to this traveling wave solution. So if you take a particle configuration under this stationary distribution for n very large, then with high probability the density of the particles is close to the shape of this traveling wave solution. And this is sometimes called these results would be called a selection principle, in the sense that both the PDE and the particle system, well, at least it's conjectured that both the PDE and the particle system select the same traveling wave to determine their long-term behavior. So as I said, these two results are currently not known. But so what I'm going to talk about in the second lecture is another particle system called the Brownian Bees. And for the Brownian Bees, we actually do have all of the results corresponding to these results. So that's what I'm going to talk about next time. And that's it for today.
Okay, thank you. So we can all unmute to thank Sarah for the first lecture of the course.